The paper discusses the topotactically induced oxygen vacancy order in nickelate single crystals, specifically focusing on PR 0.92 Ca 0.08 Neo 2.75. This material was synthesized using high-pressure methods and then reduced using calcium hydride as the reducing agent. The reduction process led to the formation of oxygen vacancies, which significantly altered the electronic states in the material, potentially leading to new physical properties and technological applications. The authors employed scanning electron microscopy with energy-dispersive X-ray spectroscopy to analyze the as-grown crystals and found that the incorporated Ca content ranged from X equals 0.08 to 0.1, indicating a discrepancy between the nominal and actual Ca content. This discrepancy suggests that different growth parameters, such as increased oxygen partial pressure, might be required to achieve stoichiometric PR 0.8 Ca 0.2 Neo 3 crystals. To investigate the crystalline quality of a 20 micrometers piece broken off from a larger as-grown crystal, single crystal X-ray diffraction, XRD, was performed. The XRD data indicated a high crystalline quality and can be refined in the orthorhombic space group PBNM, consistent with PR-Nia3 single crystals and polycrystalline powders. The refined Ca content of the crystal was 8.6%, and the refined lattice parameters and atomic coordinates are presented in the supplemental material. The authors also used atomic resolution scanning transmission electron microscopy, STEM, and electron energy loss spectroscopy, EELS, to investigate the oxygen vacancy formation in the sample. They resolved the chemical composition and atomic scale lattice of the crystal, identifying a brown-millerite-like ordering pattern of the vacancies. The STEMHAADF and ABF data were recorded at probe semi-convergence angles of 20 and 28 mRAD, respectively, and collection angles for STEMHAADF and ABF images were 75 to 310 and 11 to 23 mRAD, respectively. High-speed time series were recorded, 2 microseconds per pixel, and then aligned and summed to improve the signal-to-noise ratio of the STEMHAADF and ABF data while minimizing sample damage. STEMHAADF and ABF multi-slice image simulations of the crystal along 100 and 101 zone axes were performed using the QSTEM software, with further details on the parameters used for the simulations given in the supplemental material. The findings of this study provide an atomic scale understanding of the moderately oxygen-deficient structure with delta approximately equals 0.25, which is one of the metastable phases occurring during the topotactic reduction process towards the infinite layer phase of the superconducting nickelates. The results are notably distinct from previous reports on reduced rare earth nickelates and demonstrate that atomic resolution electron microscopy is a powerful method to locally resolve unconventional crystal structures that result from the topotactic transformation of complex oxide materials. In this study, researchers investigate the topotactic oxygen reduction process in PR1XCAXNIO3 single crystals. The crystal structure transformation is examined using atomic resolution STEMHAADF imaging and EELS elemental maps. The results indicate a contraction along the 002 axis due to the removal of apical oxygen atoms, leading to the formation of a 4AP times 4AP times 2AP superstructure of perovskite. This superstructure arises from periodic changes in the intensity of the STEM image, where half of the PR atoms along the 100 projection appear elongated, while the other half remain round and undistorted. The zigzag line patterns of PR atoms alternating along the 101 direction are observed, forming a 4-layer repeat sequence, ABAC stacking. EELS elemental maps of PR, Ca, and Ni confirm the asite cation stoichiometry and uniform distribution, suggesting that strong distortions of the PR lattice are likely not rooted in an A, B site deficiency or ordering, but rather originate from other factors such as oxygen vacancy formation. High-resolution STEM annular bright field (ABF) images were acquired for imaging lighter elements such as oxygen. The distribution of oxygen ions, including filled and empty apical oxygen sites, is clearly visible by ABF imaging. The absence of image contrast at every fourth oxygen site of the pro layers confirms the vacancy ordering, while the oxygen content remains constant in neo layers. By overlaying the yellow arrows, the ordering pattern of oxygen vacancies can be clearly visualized. Half of the Neo-6 octahedra lose one apical oxygen atom, and the remaining 5 oxygen atoms are aligned along the 100 direction, forming a fourfold superstructure. This research provides insights into the structural transformations and oxygen vacancy ordering in PR1XCAXNIO3 single crystals following topotactic oxygen reduction. The research focuses on the structural analysis of PR0.92Ca0.08 Neo 2.75, a brown-millerite-type material, using STEMHOD-F and ABF imaging. The study reveals a new structural motif with Ni ions in a square-pyramidal coordination, uncommon in nickel oxide-based materials. The STEM-ABF images show a unidimensional chain of bowtie dimer units running along the 001 direction, consistent with the brown-millerite-type structure. The analysis of ABF images quantifies the Neo-6 octahedral tilt angles and Ni bond angles, exhibiting different patterns between pyramidal and octahedral layers. The pyramidal layer shows a wave-like pattern of tilt angles, while the octahedral layer exhibits a larger amplitude of tilting. The study also discusses the distribution of oxygen vacancies and their impact on bond angles and tilting of octahedra. The findings confirm the main crystal structure and alternating stacking configuration, providing insights into the vacancy order in the oxygen sublattice and distortions of the PR sublattice. The research contributes to the understanding of novel structural motifs and the effects of oxygen vacancies in perovskite-derived materials. The research paper investigates the topotactic transformation of PR0.92Ca0.08 Neo3 single crystals to the oxygen vacancy ordered PR0.92Ca0.08 Neo 2.75 phase. The transformed crystal structure contains a 4AP x 4AP x 2AP supercell and periodic distortions, as well as a zigzag pattern of PR ions along the 100 and 101 directions, respectively. The ordering of oxygen vacancies on the apical oxygen sites forms unidimensional chains of bowtie dimer units of Neo-5 square pyramids. These square-pyramidal chains run in parallel to the 001 direction, connecting with flattened Neo-6 octahedra. The authors observe a highly distorted A and B site cation sublattice, which is unusual for perovskite-related materials. They propose that the topotactic reduction of rare earth nickelates and related materials can lead to the realization of phases that might be categorically unattainable by direct synthesis methods. The study highlights the importance of further investigations to accurately determine the reconstructed atomic positions and the crystallographic unit cell, which is likely larger than the 4AP x 4AP x 2AP supercell. High-resolution synchrotron XRD and future STEM studies on crystals after prolonged topotactic reduction can provide more insights into the structural refinement and the potential transformation into a square planar, octahedral structure with a square root 5 AP times square root 2 AP supercell. The observed oxygen vacancy ordering with apex-linked pyramidal units is distinct from all previously identified RNIO3 delta lattice structures. The study suggests that the exploration of potentially emerging magnetic order in Prex Ca 1XNIO 2.75 will be of high interest. Here is the combined summary of pages 9 and 10. The authors' citations of previous research on layered perovskite oxides, highlighting their relevance to the study of metal-insulator transitions. Specifically, they reference works by Mantheram et al. 1999, and Huang et al. 2021. On the crystal structure and electronic properties of these materials. They also cite Kim et al. 2023, on the role of oxygen vacancies in modulating the metal-insulator transition. The authors then delve into the crystal structure of the layered perovskite oxides, noting that the acite cations can be partially replaced by other elements, leading to changes in the electronic properties. They reference Takeda et al. 1986, and Takano et al. 1988, on the synthesis and characterization of these materials. The authors also discuss the importance of understanding the electronic structure of these materials, citing Vidyasagar et al. 1984, on the role of oxygen vacancies in determining the electronic properties. They reference Puphal et al. 1982 on the synthesis and characterization of layered perovskite oxides with different acite cations. The authors then present their own research on the electronic structure of layered perovskite oxides, using density functional theory (DFT) calculations to investigate the role of oxygen vacancies and acite cation substitution. They present their results in Figure 1, which shows the calculated band structures of the materials with different acite cations. The authors highlight the importance of considering the spin-orbit coupling, SOC, in their calculations, citing Vidya et al. 2006, and Rehaus et al. 2012, on the significance of SOC in determining the electronic properties of these materials. They also discuss the limitations of their study, noting that future work is needed to fully understand the metal-insulator transitions in these materials.